Well, this is the problem set number 4 on electric potential, chapter 17. It's a 32 centimeter diameter conducting sphere charged to 680 volt. You have to find the surface charge density. Okay, the formula for potential due to a conducting sphere is Q by 4 pi epsilon naught R naught, where R naught is the radius of the sphere. So when you rearrange, you get Q in this form, and sigma, the surface charge density, is the total charge divided by the surface area of a sphere. So when you substitute for Q from here, you see that these terms cancel out. One of the squares here cancels out with the R naught, and you're left with V naught epsilon naught by R naught. V naught is the potential, epsilon naught is permittivity of free space, and the radius of the sphere is 0.16 in meters. So you get the answer as 3.76 times 10 to the negative 8 coulomb per meter squared. The second part of the question says, at what distance will the potential due to the sphere be only 25 volt? Once again, this time you have to use formula for potential, obviously, and rearrange it. We have the value of Q now. Remember, from the top we have the value of Q, which we substitute here, and then put 4 pi epsilon naught R. You end up with this. That's the radius of the sphere, 0.16. 680 is V naught, which was the initial potential of the sphere, and then 25 is what is given. So you get 4.35 meter. In the second question, you have to estimate the electric field in the membrane wall of a living cell. The wall is 10 nanometer thick and the potential is 0.10. So intensity, assuming it to be uniform, is voltage divided by distance. So 0.10 divided by nanometers converted into meter is 10 times 10 to the negative 9, which gives 10 to the 7 volt per meter. In the third question, a 25 microcoulomb point charge is placed 6 centimeter from an identical 25 microcoulomb point charge, and you have to find the work required to move a test charge of 0.18 microcoulomb from midway to a 0.1 centimeter closer. So you have two configurations and you have to find the difference in potential energy between the two configurations. The formula for potential energy is 1 by 4 pi epsilon naught Q times the other charge by the radius or the distance. So initially, when it was midway, the distance was equal from both the charges. That's why you have d by 2 and d by 2 here. And actually there is a third term which I have not written, which will cancel out when you take the difference. Now, to find the final potential energy, you see that it moves closer to one of the charges, so the distance is now smaller by how much it moved. But yet from the other charge, it is that much further away. That's why you have an increased distance. And then the work is the difference in potential energies. Therefore, you take the final potential energy, which is UF, this whole term, minus UI, which will be twice this term. You see that? It's two terms added together, that's why it's 2 times that term. And then you can take out the common factor, which is 2q times q by 4 pi epsilon naught. And then you have this inside. And finally, when you substitute, remember that 1 by 4 pi epsilon naught is 9 times 10 to the 9. So finally, when you calculate, you get 0.34 joule. Do remember that this Q is 25 and the small q, which is the test charge, is 0.18. Both of them are in microcoulombs, and so there's a 10 to the negative 6 with each one of them, which together is 10 to the negative 12. And all distances have to be taken in meters. That's why you see 0.04 and 0.08 and all that. Okay. In number 4, you have to find out what voltage must be used to accelerate a proton so that it has sufficient energy to just touch a silicon nucleus. Now, assuming that all the energy is potential when it just touches, we know that the work done, or the kinetic energy that it had before when it was far away, is given by E times the voltage, where E is the charge of the electron. And when it is just touching, the potential energy is K, which is 1 by 4 pi epsilon naught, which is K, Q1, that's the electron, times Q2, the charge of the nucleus, by the distance between them. Remember that the distance between them now is going to be the sum of the radius of the nucleus and that of the proton. That is why you have the two added together here to give you the total distance. And when you plug in all the numbers, you get 4.2 million volts. That is how much voltage is required to accelerate a proton so that it has sufficient energy to just touch the nucleus of silicon. And this is number 5. You have a 7.7 microfarad capacitor charged to 125 volt, which is then disconnected and connected to an uncharged capacitor. The final voltage on each is 15, which means they are connected in parallel. You got to find the value of the second capacitor. The total charge is going to remain the same after you connect them. So I'll explain using this method, which is easier. The final voltage, you know that voltage is charge divided by the capacitance. The total charge stays the same, it's Q1 plus Q2, conservation of charge. And when you connect them in parallel, the equivalent capacitance is C1 plus C2. So all you got to do is 15 is equal to the charge on the capacitor. There's only one that had the charge, and that will be the product of its capacitance, which is 7.7 times 10 to the minus 6 multiplied by the voltage. So that is Q1. In fact, Q2 is 0. And then the sum of the two. So when you rearrange this and calculate, you simply get 56 microfarad. Now all that I've written here is just another way of writing the same thing. So you can see the initial charge is equal to the final, and charge on the only capacitor which was charged is that much, and then the final is the sum into VF. So it's basically the same done in two ways, and here you'll have to separate C2 and find it. So the answer is 56 microfarad. In fact, the important point here is that the total charge is conserved and the potentials are equal. In the sixth one, which is a very simple question, a 16 microfarad capacitor was supposed to be inserted into the circuit, but somebody just used a 5 microfarad. So what can the technician do? Just put 11 microfarads in parallel with it, because the equation for equivalent capacitance in parallel is C1 plus C2. In the seventh question, two capacitors when connected in parallel produce 35, and when they are put in series with each other they give 5.5. So you see the two equations, and this one can be written as C is equal to product divided by the sum, and we can substitute for C1 plus C2 as 35, and then when you rearrange you get the product as 192.5. So you got two equations. The sum of two numbers is 35 and the product of the two numbers is 192.5. On solving these two equations by substitution, of course you're going to get a quadratic equation, and when that equation is solved you get C1 is 28.2 and C2 is 6.8, both in microfarads. In the eighth question, a 3500 picofarad air gap capacitor is connected to a 22 volt battery, and then a piece of mica is placed between the plates. How much extra charge will flow from battery? Now Qi is the initial capacitance times the voltage. Remember that in this case, because the capacitance is still connected to the battery, the voltage will not change, and the final capacitance becomes K times Ci, where K is the dielectric constant of mica. Therefore the final charge would be the final capacitance times the voltage. Now to find the additional charge, take the difference between the final charge and the initial, which is mathematically Cf minus Ci, and Cf is KCi. So when you substitute for Cf as KCi, you can take out the common quantity, which is CiV, and then substitute mica. Dielectric constant is 7, and it's a 3500 picofarad, which is actually 3.5 times 10 to the negative 9 farad. So you see that the additional charge that flows is 4.6 times 10 to the negative 7 coulomb. In the ninth question, two 9-inch pipe pans, 5 centimeter, kept 5 centimeter apart, in fact. Try to make a homemade capacitance. You got to find out the capacitance. It behaves like a parallel plate capacitor. The only difference is that the pipe ends are circular. So to find the area, you have to use pi r squared. So that's the formula for capacitance. Epsilon naught pi r squared by the distance, all in meters. Here you see how inches has been converted into meters. 1 inch is 0.0254 meter. So when you do that, you get the capacitance as 7.265 picofarad. In the B part, you have to find the charge on each plate. The charge on each plate means the charge on the capacitor. And charge is the product of capacitance and voltage. So you take the capacitance, multiply with the voltage, which is 9. You get 6.54 times 10 to the negative 11 coulombs. In the C part, you've got to find the electric field halfway between the plates. Electric field is the voltage divided by the distance. 9 divided by the distance between them is 5 centimeters, and that you get 180 volt per meter. And the D part says the work done by the battery to charge the plates. Work done is actually the potential energy of the capacitor, which is 1/2 Q times V in this case. So you have the charge and you have the voltage. You get 2.94 times 10 to the negative 10 joules. And the part, which is the values, above values change if a dielectric inserted. The capacitance changes, the charge on it increases, and energy changes, but the electric field does not change, because electric field is the ratio of the voltage to the distance, and both are constant. Now in the 10th question, the electric field between the plates of a paper separated capacitor is given, and you have to find the capacitance and the area of each plate. Okay, charge is product of capacitance and voltage. Voltage is ED, so we can rearrange that to get C is Q by ED. Because the electric field is given, we need a formula which has the electric field in it, which we have got now. And now all you got to do is the charge in microcoulombs. That's why it's 10 to the negative 6 there, divided by the field that's given and the distance in meter, of course. And you get 4.82 times 10 to the negative 9. To find the area, just go back to the formula for capacitance. Parallel plate capacitance is K epsilon naught A by D, rearranged to make A the subject, substitute the values. And you get 0.283 meters squared. I hope you understand all these problems. Thank you.